Hello and good morning, everyone. Good afternoon to some of you, and maybe even good evening to others. Whenever and wherever you're watching this, welcome. This is week 3 of QM. This week, we are going to be talking about measures of dispersion. And in particular, we are going to talk about four types of them. Namely, they are range, interquartile range, variance, and standard deviation. Now, before we get into the details of how we could calculate them, let's briefly discuss what a measure of dispersion means and why we might be interested in calculating or finding out what they are. So recall from the previous week that a measure of location or a measure of central tendency gives us the typical or most representative number we have from the dataset. However, that alone does not give us a complete picture of what's going on in the underlying data that we have. We might also be interested in how far away the other data points are from this measure of location. So in essence, a measure of dispersion measures how dispersed or spread apart this data is from this central point. It also shows us how reliable the conclusions that we make from using our measure of location are. So in general, the lower the dispersion, the closer the data is bunched around this measure of location. And measures of dispersions are used in a variety of fields and disciplines. For example, economists can use it to measure income inequality. Quality control engineers use it to specify engineering tolerances. Investors use it to study price bubbles. Gamblers even could use it to predict the chances of winning their next game, and etc. Pollsters might use it to compute the margin of error that they get from polling. Just like last week, we are going to talk about measures of dispersion within the three data structures that we had, namely untabulated raw data, tabulated ungrouped data, and tabulated grouped data structures. So let's discuss range. Consider the example below, where a student can take one of two routes to get to the university, route A and route B. Now, if we were to calculate the mean and median of these two routes, we'd get exactly the same number, that is 15. So just by measuring their mean or median, it does not give us uh, a measure that might tell us which one is more preferred over the other. But if you look at route A, you can notice that the numbers are a bit closer to each other, so that they are a bit more consistent, and as a result, slightly more preferable to route B, where you can see that if you take route B, then the time it takes you to get to university can range anywhere from 10 to 20 minutes. So what we do is we take the range of both of these routes to show us which one is less dispersed and more preferable than the other. So to calculate the range, all I do is figure out what the maximum and the minimum values that I have for my data set, and then I take their differences. So from route A, I can see that the maximum number that I have is 17, and the minimum number that I have is 13. So for route A, uh, basically the range is 17 minus 13, which is equal to 4. Now, if I do the same with route B, the maximum number or the maximum time it takes for a student to get to the university using route B is 20 minutes. The minimum time it takes is 10 minutes. So that would be 20 minus 10, and that would give me 10 minutes. So you can see from this example here that route A has a smaller range, and as a result, it's more consistent, it's more predictable, and is slightly uh, more preferred than route B to get to the university, at least for this particular student. So this is uh, basically a formulation of what I have just said right now. In some situations, the outer values, that is the minimum or the maximum values, could take on extreme numbers. In that case, calculating the range between the lower and upper quartile is more appropriate because this outlier will cause the range to be misleadingly large. Let's consider example 2 from last week's lecture. There was a student that was going to the university, taking the typical route that he takes and recording the time it takes for him to get there. Now you'll notice that in the last day, it took him an unusually large amount of time, and that might have been because of some accident and etc. Uh, so we don't really know, but in general, it took him a long time. Then there is an alternative route that he's now considering to take instead of this one. And if we calculate the range for the typical route and the alternative route, we'll see that the range for the first route is 34 minutes, and the range for the second one, for the alternative, is 18 minutes. Now, if we just look at both of these ranges by themselves, it might suggest to us that the alternative route is more consistent and as a result might be preferred over the typical route. But if we look at the numbers by themselves, we can intuitively get a feeling that the typical route is actually preferable over the alternative route. So what we might want to do is to take away the outliers and then consider them again. So what we might want to do is calculate the interquartile range. Uh, Now, to figure out what the upper and lower quartiles are, let us just arrange them in order. That's going to be 9, 10, 11, 12, and 43. So the lower quartile is this number, the upper quartile is this one. So our interquartile range for the first root is going to be 12 minus 10, which is equal to 2. Let us put the alternative roots data into an order as well. So that's going to be 11, 13, 15, 17, and 29. So the lower quartile is 13, the upper quartile is 17. As a result, the interquartile range for the alternative root is 17 minus 13, which gives us 4. So that would mean to suggest that the typical root's interquartile range, that is the range of the most common values that it has, the center 50% of its values, is bunched up much closer than the alternative root's values. And that might suggest that actually it's not the alternative root that has less dispersion around its values, but it might actually have been the typical root. The range only considers the outer values. While the interquartile range does discard the outliers, it still only considers the quartile values. What if we wanted a measure of dispersion that would consider every data point that we have? Well, we can do that with variance. Variance is the average standard deviation from the mean. Let's plot the travel times of the alternative route on a graph just first to have a visual perspective on it. So the mean, which was 17, is represented by this solid line. Then I have here a dashed line which represents the distance of every data point that we have from this mean. Now what we want to do is to find the average distance of all of our data points from this particular mean. So if we were to do that, we would calculate the mean, which in our example is going to be 17. Then what we do is we take the difference between each of our observations and the mean, which we do in this column over here, and that's going to be -2, -4, -6, and 12. However, notice that if you try to sum them all up, you actually get 0. Right? And I would also like you to think about why that would be the case. It's actually because the mean is such a point where the average distance from all of our observations is going to be 0. That's part of what we want to do when finding the mean, actually. So in order to remove the sign and to make sure that when we're adding them up, they don't cancel each other out, we take their square. That is, we multiply it by itself to remove the sign. And we do that in this column over here. Right? And after squaring them all up, we add them up, and that would give us, in this case, 200. Then what we do is we divide it by the number of observations that I have. In this case, that's going to be 40. So the formula for variance is this over here, which is basically what I have just done right now. So first of all, we find what the mean is, the central point. We find the difference between every data point that we have and this mean. We square it, and then we add all those numbers up. Once we have finished finding all those numbers, once we have finished adding all those numbers, we divide it by n, the number of observations that we had in our data set. And in this case, it is 40. However, notice that the unit of this variance is square of the underlying. That is, for example, in our case, where our units were minutes, then the variance of this particular data set that we have is going to be 40 minutes squared. So that makes it a bit difficult to explain it to others or to even understand it ourselves. Luckily, what we can do is we can take its square root to remove that square unit and go back to the underlying units that we had, in this case, minutes. And if we do take the square root of the variance, then what we are finding out is our standard deviation, right? So in our example, our standard deviation is the square root of 40, so that would give us approximately 6.3 minutes. Now, 6.3 minutes, you can interpret it as the average distance from the mean. Although it's technically not that, it is a good way of trying to have a grasp on excuse me, on what standard deviation is. So in this case, the average distance from the mean of 17 of these typical roots was 6.3 minutes. Note here that the formula that I showed you, while this also works, there is actually a less computationally intensive calculation formula to calculate it, and that is given by this one over here. Now let's talk about tabulated ungrouped data structures. Again, if we want to find the range, what we do is we find the maximum number, we find the minimum number, we take their difference. That shouldn't be that difficult to do in this situation. The maximum number that we have is 8, the minimum number that we have is 3. The difference between them is 5. That is my range. Now let's look at interquartile range. Again, interquartile range is basically the range between the lower quartile and the upper quartile. So recall from the previous week that our lower quartile in this instance was 4. That was, we take n plus 1 divided by 4, and that's going to give me 31 divided by 4. That would give me the 7.75th value. So we could take that to be the 8th value. Our eighth value is going to be within this group over here, so that's going to be 4. My upper quartile is going to be 3n plus 1 divided by 4. That would be 23.2 fifth value, right? So we could take that to be our 23rd value. My 23rd value is in this group over here. So this is my upper quartile, right? And then I just take the difference between the two, and that will give me the interquartile range. Finding the variance for tabulated ungrouped data structures is similar to that of untabulated data. The only difference that we have is instead of the raw data, we have the frequency information from our observations. So instead of calculating the square deviations individually, we'll have to take into consideration the amount of times our particular observation has occurred. So in this particular example, the mean is 5.3. So once I have 5.3, I subtract it from all of the observations that we have. So that is happening in this column over here. So my observation was 3. So 3 minus 3.5. Once I found that, I square it. That would give me 5.1. Now that is only for one observation. And in here we have 4 observations of 3, so that would be, I would multiply my result of 5.1 with 4, so that is done in the next column, and we get 20.06. Now notice it's not exactly the same numbers, and that is due to rounding that we have here. And I continue doing that one by one through all of my data sets, and then I come up with, or I get as a result, all these numbers that I have. Then it becomes similar again to untabulated data structures. I just add them all up, and that is signified by the sigma symbol over here. And then I divide it by the total number of observations. In this instance, the total number of observations is equal to the total frequency here, because that is exactly what it's counting. So in our example, that is going to be 63.9 divided by 30. So my variance for the number of TV sets sold is approximately equal to 2.1 TV sets squared. Now again, this unit of measure is a bit difficult to grasp, so we might want to get rid of the square that we have. So what we do is we take its square root, and if we do take its square root, that would be the standard deviation. So in this instance, the standard deviation is very close to 1.5 TV sets. And if we look back into our data set, what that basically means is that the average deviation that we had from the mean is 1.5. So if we look actually at our data set here, so the mean minus the standard deviation, that is 5.3 minus, let's say, 1.5, that approximately gives me 4, and 5.3 plus 1.5, right? So this must have been a 5 actually. Approximately gives me 7, right? Let's say 7. So if we look at the range over here, that is from 4 till 7, you can see that the majority of my data is contained within that group. Now let's talk about tabulated grouped data structures. Again, the concept of range is not that difficult. However, with group data structures, we don't actually have data points, we have ranges. So when we are taking the minimum of our range, what we do is we take the lower boundary of our first group for the minimum. So in that case, that's going to be 0. And for the maximum, we take the upper boundary of our last group. That's going to be 50. So their difference is going to be 50. And that is my range. Upper quartile has a similar concept, but this time we're finding the range between the two quartiles that we have. Right? So this is an example from last week, and the lower quartile was 12.8, upper quartile was 26.3. You just take, again, the difference between them. In our case, the interquartile range is 13.5. Lastly, let's consider the variance for tabulated grouped data structures. Now, again, remember that we have a range instead of a single number. So we'll have to make an assumption, and the best assumption that we can make is that our observation lies exactly in the middle of our range, and we'll call that the midpoints. And we have the midpoints over here in this column. This formula, this computationally less intensive formula for variance, is a bit quicker in finding the variance and consequently the standard deviation. That's because I don't have to subtract each of my data points from the mean n number of times. That would save me some amount of time in trying to calculate this thing. So that might also be something useful for you. Perhaps in your quiz, in your exam, or maybe in real life when you want to calculate the variance or standard deviation of something. So to do that, I will have to take the square of all of my midpoints. So these are my midpoints that I have. Their square is in this column over here. Right? And then I start multiplying my midpoints with the number of observations that I have for that particular range. So that's going to be in this column over here. Finally, I will add all of these numbers up, which is basically what this sigma symbol is signifying. As a result, I will get this number over here divided by the total number of observations. That's going to be 50. So this is what I have here, minus the mean squared. So in this instance, the variance is 99.7. Again, recall that its units are square of the underlying. So the variance is $99.7 squared. And again, that doesn't yield itself to easy interpretation. So what we do is we remove the square from the units. We do that by taking the square root, and the square root of the variance is the standard deviation. So in this example, the standard deviation is approximately equal to $10, so it's 9.99. And again, if we look back into the table that we have, so the mean was 19.9, so we could say that it's approximately in this point over here. And if we subtract or look at one standard deviation below this mean, it's going to be starting from this point up until here. And if we look at one standard deviation above the mean, that's going to be until 30, so until here, right? So we can notice that within this small range, we actually have more than half of our data. So in this case, that's actually equal to 34 out of the 50 total data that we have. That is approximately 68% of our data. And that is usually the case within one standard deviation plus or minus from our mean. More than 50% of our data usually resides in that range. This is it for week 3 of QM. Hope to see you guys next week.